Okay, so hello everyone. Welcome to the channel of IEEE Student Branch Chapter of Netaji Subhash Engineering College. My name is Hoymanti Datta and I am from the Computer Society and the Department of Computer Science and Engineering first year. I would like to warmly welcome you all to the second day of a series of talks focusing on the theme of quantum computing for beginners, academia, and industry. This event is organized by IEEE Computer Society Student Branch Chapter in association with IEEE Computational Intelligence Society Student Branch Chapter of Netaji College. With us, IEEE distinguished visitor, Dr. Amlan Chakrabarti. He is a full professor in the A.K. Choudhury School of Information Technology at the University of Calcutta. He did his MTech from the University of Calcutta and his doctoral research at the Indian Statistical Institute, Kolkata. He was a postdoctoral fellow at the School of Engineering, Princeton University, USA. He has published around 150 research papers in referred journals and conferences. He is a senior member of IEEE and ACM, Speaker of ACM, of IEEE CEDA India Chapter, Member of International Water Association, Vice President of Society for Data Science, and Life Member of CSI India. He is the Associate Editor of the Elsevier Journal of Computers and Electrical Engineering and Guest Editor of Springer Journal of Applied Sciences. Among his numerous accolades include the prestigious D.S.T. Boys Cast Fellowship Award in Engineering Science, Indian National Science Academy, INSA Visiting Faculty Fellowship, Hemant Visiting Professorship from the University of Cambridge, and Siksha Ratan Award by Department of Higher Education Government of West Bengal. So, without further ado, please welcome Professor Amlan Chakrabarti.
Yeah, thank you, Hoymanti, for this brief introduction. And thanks to the IEEE Computer Society and IEEE Computer Society Students Chapter, Netaji Subhash Engineering College, for inviting me and to give me the opportunity to speak to all of you. And the topic what I will deliver today or I will discuss with all of you is a very interesting topic and is a very upcoming topic in computer science and electrical engineering, and also it takes care of the concepts of physics and mathematics. So I hope that my lecture will be uh, all of you will like my talk, and it will create enough interest for all of you. So let me share my screen to start my
Okay, sir.
presentation.
So, without further ado, the screen is all yours. So,
Thank you,
okay.
Hoymanti. Yeah, thank you. So I hope I will just start my presentation mode. Yeah. So I hope my screen is visible to all of you, right? Is my presentation is visible to all of you? Is my is my presentation is visible? Can you just tell me or let me know?
Yes, sir.
Hoymanti?
It's perfectly visible.
Okay,
Yes, sir.
okay,
It's
great, great.
visible.
Okay, fine. So dear all participants, today my lecture will be on programming techniques for quantum computation, and I have actually given it a short form that let's quote quantum. So what I will do in this lecture is that I will try to give a brief overview of what is quantum computer. I will try to brief you about the basic postulates of quantum computer, and then I will try to introduce you the fantastic platform or the fantastic podium of quantum computer program. Okay, and I will try to also help you to give you some examples, right, on the coding platform, the IBM Cascade, so that in this lecture you are habituated of what is coding on quantum computers, and you can carry forward this knowledge for further development. So, so before I start my discussion, I would like to pay my regards to two of my mentors, the Professor Shushmita Shurkole of Indian Statistical Institute. She was my PhD supervisor, and still I'm collaborating with her in some of the PhD and research projects. And also my postdoc supervisor, Professor Netaji from Princeton University, where I stayed for 1.5 years and worked with him. And we developed a very, very important and very prior tools. Many of the tools have inspired the next generation of quantum computing. And these are my students. I have a very vibrant, very active, knowledgeable, and working group at the School of Information Technology, known as A.K. Choudhury School of Information Technology, University of Calcutta. We work in multiple domains of quantum computing, like quantum CAD, which is called computer-aided design for quantum circuits, quantum algorithms, quantum machine learning, and quantum cryptography. Our students have founded the first quantum startup in Kolkata, which is called the QRD Labs. And Mrityunjay is spearheading this lab along with my students Nivedita and Devdeep. They are working with him, and they are also doing research with my group. I have also very two dynamic and very two bright students who are now very established persons from industry, Amit Shah and Shoikat Basu. They are both senior consultants at Atos Pune, and they are doing perfectly. They are doing great both in industry and in their research. And also I have PhD students like Bipulan, and also a couple of more PhD students. Regarding the collaborations, the students who are interested, or the faculty members, the researchers who are interested to work with us, we have a collaboration with the IBM Quantum through the IBM Quantum Network. We are one of the first institutes in India who will be the part of this IBM Quantum Network. We have also very good collaborations with Princeton University, Sunny Buffalo, US, University of Bremen, Germany, Indian Statistical Institute, and obviously Iwate Prefecture University, Japan, where we have a Department of Science and Technology Indo-Japan project on quantum computing. So this is all that someone, if you want to collaborate, if you want to connect with us, please connect. We have a fantastic group, and I normally invite the interns in my group also for participating in the various activities we do at our lab. So the agenda of today's lecture is the fundamentals. I will start with fundamentals of quantum computing, and then I will move on onto the basic concepts like the qubits and quantum gates and circuits. And then the core part of today's lecture, which is the programming techniques for quantum computing, I will try to demonstrate to all of you that how we can use the Cascade, okay, to build our quantum programs. So what are quantum computers and how they are different? This is a big question, and I think this is now very well answered in various forms. So this is a migration of hardware technology. So our computer hardware technology, which was initiated by electrical and mechanical and then electrical devices, were transformed into electronic circuits by the discovery of silicon, or the semiconductor. And we have a long era of computer hardware, which are nothing but VLSI circuits, or rather VLSI chips, which are still which are still working strongly to support our computing need. But the era what we are going towards, okay, or already there are a lot of steps have been taken, is the era of quantum computers. The difference between the way we compute in the classical computing, which is the on silicon computing, and the quantum computers is that this is the computation which is done at atomic scales. So, so if you look into the VLSI sizes of the device, the present dimensions of the VLSI devices, right? You know that the present dimensions are touching 8 nanometer or maybe 5 nanometer, which itself means that the dimension of our devices are on the monoatomic thickness, okay, or maybe maximum 2 atoms. So now the question is, when our devices or when our materials are of that dimension, okay, can we still go on doing the classical computing or the classical electron transport phenomenon? And that actually pushed us towards that, hey, can we not use the atomic principles which is inherently quantum, and can we not go to that regime, right? And that push is one of the push. It's not that that is the only push which initiated quantum computer, but miniaturization of electronic hardware, okay, from the multiple atomic scale, multiple atoms to the single atoms or subatomic scales was one of the push which initiated quantum computers. And if I have quantum computer, it means that I am working with those atomic states of matter. Instead of bulk states of matter, we're working with atomic states of matter. And that's why this migration actually shows, this particular diagram shows you that the entire computing, the computing resources are now your atomic states, right? How they are utilized, okay, there are a lot of ways they can be utilized, and that's what is the quantum computing, okay? So quantum computing is basically utilizing the atomic states of matter, right, which are essentially quantized, right? And that's why it is called, or subatomic states also. That's why it's called quantum computing. That is you are trying to define your computational process to the states which are essentially quantized. Now how they are different? They are different because the quantum phenomenon itself incorporates certain postulates which are not available or which we cannot have in the classical domain, like the postulates of superposition, entanglement, and interference. These three phenomena in this dimension of matter gives certain benefit, okay, in modulating or transforming the quantum state. Because what is computation? The computation means your state of a system will be initiated with a particular definition, and through certain computational steps or operations we tell, it will lead to an output state of your machine. And that if we try to do in terms of the atomic state, which means you have a distribution in the atomic domain or subatomic domain, and you try to have some sort of phenomenon by which the distribution gets modified, and slowly and steadily it leads to a distribution, which your result distribution, that is computation, right? And that is what is computation at the atomic scales. And while we are modifying these distributions, we are having the support of three phenomena, which are called superposition, entanglement, and interference, which in some way makes the quantum state a more valuable computing platform in for some of the algorithms. It's not that for every algorithm we have quantum speed up, right? Obviously, we have, okay, it is proved that for many of the useful algorithms, we have a quantum speed up. And this quantum speed up is basically due to the phenomenon what happens in the quantum domain, which are absent in our normal classical computing, right? So that's why, and I will try to have a little bit more on this as I go forward in my presentation. So let us look into the basic understanding of what is quantum computer by understanding what are qubits. So we know that bits, right? Bits are the unit storage elements in our classical computing domain, right? If we want to store a data, right? So I think that we store a bit. That's the smallest dimension of a computing state. So like this bit we have in the classical computing, the equivalent is the qubit in a quantum computer, right? And what is a qubit? If you see these diagrams, right, you see that this is basically called a Bloch sphere. Okay, this particular sphere is called a Bloch sphere. Okay, and this Bloch sphere, if you look, if you see that on the surface of the Bloch sphere, I have given several, several marks, and each of these marks are probable states of your qubits. And these states, the difference between the states of a bit and a qubit is that in the case of a classical bit, the bit can be either, this can be considered as a 0 state, and this can be considered as a 1 state. Okay, but you can have, instead of 0 and 1, which is this is the state of 1 in the quantum computer, and this is the 0 in the case of quantum computer, but you have several other possible states like this state, and the states what I've already marked. This has a projection on both an 0 and 1 axis, and these states are called superposition states. Okay, and that is actually the qubit can actually have, or we can actually have a qubit instead of the pure states of 0 and 1 like the classical computer, the classical bit. We can also have the states which can be a superposition of 0 and 1, right? And that's actually the one of the advantages of quantum computer, because with the superposition states we can represent a larger amount of information with a less amount of resource in the case of quantum computer compared to the classical computer. So let's see that how the resource scales up in quantum computer and classical computer. So in the case of a classical computer, if I am trying to use a classical register to store my data, right, and I know that it is a linear, which means that if I have to store n bits of information, or if I have to store n states, right, I require n registers. This is pretty standard, right? If I have to store 1 state, I require 1 register. If I have to store 2 state, I need to 2 register, and this also. So it actually scales up in a linear way. So the resource what you give, and the resource what the computational addition of resource is a linear. So if you give it's the x amount of, if you add x amount of resources to your computer, the actual resource enhancement is also x. Vis-a-vis in a quantum computer, Okay, due to the superposition principle. Okay, if you have one bit, okay, you see a one bit can be represented as a superposition of a 0 and a 1. So which means that a one bit can be represented as a superposition of two values. Okay, two states. And similarly, if we have n states, okay, they will have a sort of tensor combinations of this. Each of the space, each of the state space will combine as a, okay, in a tensor form. And actually for n qubits of resource, you can have 2 to the power n dimension of your data space. So you see that the resource scaling up of resource in the quantum is actually in the form of exponential dimension. And we know that at the present paradigm of computing, right, where we have the algorithms which are working on large dimensions of data, we get stuck. Why we get stuck? Because we cannot provide the resource, okay, to process our data or to store our data, okay, uh, because the resource is to, okay, the input and the output in terms of resources linear in case of a classical computer. But in case of quantum computers, so there are, so this is one of the advantage, or this is one of the uh, most prominent feature of quantum computer, that they can scale up the resource exponentially, right? And that particular way of scaling up the resource actually helps to execute a very costly algorithm which is there in the classical space, that in the quantum space, in a uh, very easy way, right? Because you have an exponential amount of resource to compute that problem. Now, when we look into the way the resources are physically, so when I tell that, hey, this is a quantum computer where we can have some quantum states, and these quantum states can grow exponentially with the addition of, okay, of each qubit. Then you may question me, sir, what is this? What are these qubits physically? Now, there are different technologies, right? Actually, when I was at Princeton, we worked with 5 technology verticals. And I think that there are more technology which has come up, and some technologies which have been proved that they will be not be much worthy. So what I tell you now is what are the technologies, okay, which are available in a very brief manner. So trapped ions are one of the technology where the flow of the ions, okay, flow of the ions in a trapped quantum channel, right, can behave as a quantum state, right? Similarly, we have the superconducting loops. Okay, just to let you know, superconducting loops and trapped ions both show a high promise, right, and actually being used by the existing quantum hardware that we have, okay, and so are very promising technology. Why I'm telling they're very promising technology? Because all these technologies have proved to be good and fine for a quantum system which consists of a qubits, of a few number of qubits, maybe 50 or 100 qubits. But to scale this up, okay, and to make it really competitive, okay, to address the scenario where I tell that quantum computer can find the prime factors of a large number, right, in a very easily, and in that process will collapse the RSA. To go into that scale, we require a quantum computer which are of 1,000 or maybe 2,000 qubits. So I tell promising technology because this all technology shows a promise maybe from 50 to 100 qubits, but if they can scale up to 1,000 or 2,000 qubit, and then where the quantum supremacy comes, okay, the quantum supremacy comes and the classical computers are straight away outperformed, which is a target. So to reach in that level, obviously, I think there are more technological advancements are still required, and that's why we have the quantum computers in a very limited scope of operations. But having said so, being associated with quantum computing for the last 15 years, starting from my PhD, when I started my PhD, there was no notion of quantum systems. The notion was only that we can develop certain systems, okay, which can behave quantum mechanically, which can have certain properties. Okay, when I was at Princeton during my postdoc, the scenario was that here people are really looking into and try to think on systems like 5 qubits or 2 qubit systems, and those were coming up. But now at present, when I have actually 5-6 PhD students with me and some collaborations, now people are showing a great promise. Okay, I'm trying to work more on this particular domain because now we see that, I will come to that part also. Now we see that that means a large number of parties have come into the ecosystem of quantum computing, both from academia as well as industry, and I think over the time period of 2 to 3 years, okay, the projection is that quantum computer to the scale what we require, okay, will be coming up, right? And then every algorithm, that means then in every the applications, there will be a push that the applications should be ported to quantum computers, right? Because they are now fine, and that's why we need to generate our knowledge in this domain, so that we can perform, or we can actually use those machines to do our computation. So like the superconducting qubits and ion traps, the other promises are silicon quantum dots, okay, which are also existing for a long time. Topological qubits is one of the recent standards of quantum computing, and diamond vacancies is something like, I think, nucleus, the neutral atom sort of stuff. This is also some upcoming technology. So these are some of the technologies which people in the research labs are trying to develop and trying to scale up. Some are available in the commercial machines, and some are showing good promise, so that they can actually be taken into consideration. So now let us look into the computation part of this story, okay, of the story of quantum computing. To understand the computing scenario, what happens in a quantum computer, what we need to know is the basic operators what we have. And obviously the basic operators are represented in terms of the basic quantum logic gates. I will not discuss in details also on this, because the more focus of today's lecture is quantum programming. But just to set the stage, I am giving this introductory concepts to all of you. So these are the gates, okay, and if you look into the gates, some of the gates are very similar. Like if you look into the gate X naught, right? This is similar to a NOT gate. Okay, means if you operate this operator to a state of 0, it will produce 1. Okay, if you operate it on a state of 1, it will produce 0. So what it does, it actually operates on a state 0 and produces state 1, right? And similarly operates on a state 1 and produces a state 0. Okay, very similar to a classical NOT gate. So only that means if you look into carefully, that these particular gates, all the gates what I have shown, okay, are actually 2x2 gates. Because all these gates are single qubit gates. So the normal logic is that if you have a gate which is of so for a n qubit system, the gate is 2 to the power n cross 2 to the power n. Okay, so what I have, all these gates, which is a x naught gate, which is a phase gate, y gate, which is a Pauli y gate. This is called a Pauli y. Okay. Okay, Pauli y gate. This is a Pauli z gate. This is an S gate. This is a T gate. This is a Hadamard. This is very, very important. This gate leads to superposition. Okay. Okay, this gate leads to superposition, and these are all the gate libraries. You can go to any reference and you can find out the gate libraries which are available, and all these gates. Okay, one other important thing you have to remember, that these all gates are unitary transformations. Okay, unitary transformation means U and U dagger is an identity matrix. So this is also a postulate which comes directly from quantum mechanics, that any quantum operator, okay, should be an Hermitian space, right? And it should be a sort of unitary transform. Okay, unitary transform means you can always find the complex conjugate of that particular operation, and obviously if you can get the complex conjugate, then the product of two is I. So there are two things you need to remember whenever you find a quantum gate. Okay, one is that a quantum gate should be of dimension 2 to the power n cross 2 to the power n. Okay, this is always a square matrix. And what is this n? This n defines that on how many qubits this gate can work upon. So the example gates are all 2 cross 2 gates, so which means that n is equals to 1 here. And these are all single qubit gates. But you have 2 qubit gates. You can generate 3 qubit and 4 qubit gates also. Okay, logically, not they might not be there, and they might not be physically workable because you need to decompose them into some primitive gates again. But logically, you can have a 2 to the power n plus 2 to the power n gate. And the second thing is that all these gates are unitary transforms. Okay, they define unitary transformations. Okay, this is due to the principle of quantum mechanics. Now let us look into that. What is computing then? Right. So computing. Okay, obviously, when I'm demonstrating this computing is called quantum gate computing. Though there is another way of quantum computers which are called quantum annealing based computing. Okay, which is more like an optimization application, solving an optimization problem, which I am not discussing in this particular lecture. Right? In this particular lecture, as my target is to make you habituated with the quantum programming platform, so I thought that a discussion on quantum gates and quantum circuits, or quantum computing based on quantum gates, will make you easier to understand quantum programming. Right? And that's why this is the these examples I am demonstrating. So let's go into quantum computing. So what is quantum computing? If you look into this particular picture, okay, you will see that this particular list, okay, this particular list is your qubit. Okay, qubits actually. So you have 5 qubits here, which are presented at Q0, Q1, Q2, Q3, Q4. And what is this? This is your classical bit. Because ultimately, your world is classical, right? You have to read out and you have to come back to your classical world, okay? So So let's try to understand what this particular figure represents. So we have a set of qubits which are initialized with 0. Okay, this is the symbol which we use called ket symbol. Okay, this is the ket symbol. Okay, means you have represent 0 by this and 1 by this. Okay, so this is a ket symbol. Okay, so using the ket symbol, okay, using the ket symbol, we actually represent all the qubits initially as 0, and then these are all gets. Okay, this is a two dimension, okay, 2 qubit get. Okay, which dimension is 2 to the power 2 plus 2 to the power 2, which is a 4 plus 4 get. And this get is called the control get. Okay, where this particular circle is called the control qubit, and this operation which is called a target qubit. Okay, so this is called the control and this is called the target T. Okay, and these are all single qubit gates, like you have the X gate, H gate, S gate, Y gate. Okay, that's what we have shown these matrices in the previous slide, and this is again a stream of gates. So what do you do? This is your quantum circuit, right? This is your quantum. Actually, this is your quantum circuit. Okay, and this quantum circuit operates. Only one thing you need to understand here is that when we try to describe a classical circuit, when we tell that what is this particular axis, in the classical circuit, this axis is space, which means that in a classical operation is that this is an input, okay, which goes on to this particular gate. These two inputs passes through these gates, produces an output, and then again this output works as an input to the gate, and then again it flows. So there is an assumption of signal flow from the right to the left. Okay, and that is the circuit way we understand circuit operations. The difference in quantum is that this axis, instead of space, is time. So what it means then? It means that these registers are operated. These are the time slices: time slice 1, time slice 2, time slice 3, time slice 4, time slice 5, time slice 6. So these are all time slices: T1, T2, T3, T4, T5, and T6. So on different time slices, these particular qubits are being worked upon, right? And ultimately we come to, in this time, we have a transformation. So transformation starts from here, and the qubit states are transformed in the discrete time intervals, and ultimately the transformed register is here. In this time, I get the register which is something which has been transformed by these operations, and then we measure each of the registers. Okay, and this is called a measurement operator. Okay, so this is a measurement operator, and each of this measurement operator measures the values of these particular qubits and actually passes on to the classical domain. And this is how the quantum computation works upon. Okay, yeah, that means I know that you can have many queries on this, but within a limited scope of time, I am trying to utilize the time at best. Okay, so if you understand, so what do you need to know now? You need to know now. Okay, so what are the ways I can initialize the qubits? What are these operations actually means? I have only represented it symbolically, right? And how I can actually compute this state which comes which is generated after the operation of all these gate operations. Okay, there are standard matrix operations, okay, you need to do, and that's why linear algebra is is so important to understand the quantum computation. So you need to just understand that these are okay. You start with the initial column matrix, and then you try to operate the matrix with all these operators, and you come up to a result column matrix, right? And then you try to evaluate, measure all the individual bits of the quantum system. Okay, now when you represent this particular quantum system or quantum computing as a small bit of quantum computing in terms of gates, this is obviously a good representation or one of important representation. But the representation which is also required, okay, sorry, okay, and the representation what we actually need to pass on to my actual quantum hardware, which is my true quantum machine, okay, might be a bit different from the initial circuit description what you have generated, and that is called a transpilation, which is very important to understand when you try to execute your quantum algorithm on a real quantum machine. So transpilation actually makes your quantum circuit description fit for the specific quantum technology you are working with. And each of the quantum technology has these particular steps, okay, of how to optimize, how to understand the physical placement, okay, of the qubits, so that the entire circuit is optimized and your error is minimized. Okay, I didn't speak about error here because that's also one of the major hindrance of quantum of the scaling up of quantum circuits. Okay, the amount of error, okay, is actually proportional to the number of qubits, and it is of some times, right? Some n times the number of qubits, and that's why when you have a large number of qubits in a system, right, you need to have a very efficient error handling procedure. Why this error? Because this error is due to the interaction with the classical environment. Because though we are telling that we are working with atomic states, we will be running this on an atomic engine, but our real world is classical. So whenever we try to interact, okay, with a quantum engine, okay, we will find that this interaction involves okay, certain decoherence, and that destroys the quantum states. And this destruction is represented, okay, to the true quantum operation in form of error. And to optimize that in different technology, we need to actually reorder the circuit, okay, in terms of the actual technology, and that is called, and also the gates what we present in my high level description and the gates which are available in my technology may also vary a bit. So ultimately we may need to represent the entire quantum representation with the quantum gates and quantum libraries, okay, which are available in the particular technology. Okay, and then it comes the physical circuit optimization. This process is called transpilation, okay, which actually helps you to take your quantum circuit high level quantum circuit description to the exact quantum circuit description for the specific technology. Now let's get a bit motivated on what are the present status of quantum computing, and it's really fascinating, right? You see that there are announcements from the big players like Google, Microsoft, IBM, right, D-Wave, okay, who are doing a phenomenal contribution in the domain of quantum computing. And obviously we you all know that now the quantum computers are available in the cloud, right? Many of the quantum platforms, okay, in some scale, are being offered to the programmers or developers in the in the cloud platform, right? And that's why we are interested now to work with those quantum computing systems. And the other domain of quantum computation, apart from quantum algorithms, is the quantum communication and quantum cryptography. These are also very promising domains where we can have that means a quantum a communication, okay, of a large data, okay, and okay, giving us enough opportunity uh, to to generate a high bandwidth communication between two nodes. And secondly, it gives us a good amount of resources so that uh, we can communicate the data between two parties in a very secret way. Okay, and it is proved that quantum cryptography, okay, has more stronger, okay, has more stronger properties, okay, so that the adversarial attacks can be minimized, right? And that's why the domain of quantum communication and quantum cryptography is also very promising. The upcoming domain is quantum machine learning, right? It has been understood that the multi-dimensional space which has been generated by the quantum bits in a very simple way can actually it can be used to understand your feature space, which is the fundamental of machine learning in a better way, in a more exploratory way, right? And that also helps the machine learning. So quantum machine learning is also a very upcoming field. To motivate all of us, Government of India and Department of Science and Technology has started a national mission on quantum technologies and application, and there is a huge amount of funding has been promised under this particular scheme. So Government of India and Department of Science and Technology expects, okay, the research and the development in this particular domain should be accelerated in our country. To give it a better, to show the scenario in a better way, you see, okay, a large number of corporates, large number of organizations, okay, are now into this particular quantum world, right? They are either developing the softwares, okay, or they are actually true quantum computer providers, or they are giving enabling technologies, and there are a lot of funding and funding proposals are there, okay, to again to motivate the researchers across the world to join the world of quantum computing. Now let's move on to the most interesting part of today's lecture, which is that what is quantum programming and how I can program in the quantum platform, or let's quote quantum. So there's a history of programming languages, right? But the difference between the programming languages, what we are experienced, and the quantum is that we are now moving to a very new type of machine, right? A very new type of architecture, right? And that's why we need to actually know this platform, and to know that how we can use the constructs or use the abstraction of this particular platform, and we can utilize them in our program. And obviously lot of activities are now being going on. Okay, we are having research meetings with various organizations, research labs, as well as industries, right, where people are interested to port their programs in the quantum systems, basically due to two reasons. Reason one, quantum system can give you a better scale up. So if you have a okay, large volume of your program, okay, in terms of data or in terms of the complexity of your computation, right? Hey, can we pour it to a quantum machine, and can we try to find that whether quantum machine can give me a good result? This is the most asked question in many of our collaboration discussions. The second motivation is that, hey, can we find a particular new technique, okay, in the quantum computing, which can actually make this complex problem very easy, okay, solution, because as we are using a different type of computing platform, okay, the solution can be very different, right, and can be much easily generated than in the classical computing system, something like quantum cryptography and those domains, okay. So that's why there's an immense push that we need to know the quantum programming the quantum platform, and try to test our algorithms in that particular platform. So if you look into the platforms available, there are plenty. Okay. QCL is I think the one of the early ones, QCL and DUF. And then we have a very strong platform, IBM Cascade, which I will be demonstrating to you all. Google has a platform Circ, Microsoft have QHash, AWS, Amazon Bracket gives you a plethora of quantum platforms in the cloud platform. Rigetti has Forest SDK, and Xanadu has Pennyland. So all these platforms are actually serves the purpose. Okay, but obviously there are differences between each of the platforms, right? And when you tell that I want to run a quantum program, right, you need to choose the platform which gives you the most flexibility, right? In terms of our understanding, the understanding of our research group, right, we are one of the strongest in India in using the Cascade platform, right? Actually, again having said so, many of my students, okay, are better programmer than me in the Cascade platform, because as you know, being a professor, okay, my job is mainly to discuss or to focus or to analyze the problems, right? And students will be more as a workforce who will be actually trying to work with the problems and will trying to solve the problems. Okay. So, but just to motivate all of you, right, I will try to explain from my understanding what is the IBM Cascade and how best you can use this IBM Cascade. So what is IBM Cascade? IBM Cascade has a physical, that means this is actually developed on the basis of the real quantum hardware which IBM provides, right? I think at present IBM goes up to 50 qubits or maybe 100 qubits. Okay, can be, okay, the commercially available is, I think, 100 qubits. And for research purpose, they offer, I think, a system which is of 50 qubits. 50 qubits is normally offered to some collaborations like what we are having on the IBM Q platform. Normally it is up to 15 qubits. Okay, if you just try to connect the IBM cloud and try to connect with the IBM machine, right, you can work on a 15 qubit IBM system, right? And that I will demonstrating here. There are a lot of flexibilities in this IBM platform. You can use the normal Python 3 platform, or Jupyter Notebook, okay, and there are fantastic libraries which you can take help, by which you can build a program, right? And you can have two ways of developing the programs. Okay, one is that you can use your Python framework, okay, by just calling the Cascade package, importing the Cascade package in your IBM in your Python framework, right? And you can execute your code. The other is that Okay, you can also connect, okay, through a registered account. Okay, you can also connect to IBM, like IBM Cloud, IBM Quantum Cloud, and you can run that on their machine. Right? I will try to give you a demonstration of both of this in this part of my lecture. So this is what is an IBM Quantum Lab. I think let me move to this scenarios. So I don't know how many of you are on your PC, right? If you are on your PC terminal, what you can do, you can just Google, okay? You can just Google that. Okay, you can just Google IBM. This is IBM Quantum Login, okay? Or maybe IBM Q also you can write. So if you go to IBM Quantum Login, you can get into my account. I'm already logged in, so I think it will go to my default account. But obviously, if you don't have the initial account, there is a process you can just follow to have that. Okay, right. And obviously, you need to install the Qiskit. Okay, in your Anaconda, okay, the platform what I prefer in Python is Anaconda, so you can install the Qiskit in Anaconda platform, and you can just start doing that. Okay. So let me start my Anaconda platform. Let me close this. Okay, so before going into this, if any one of you have any questions on the preliminary part of quantum computing and quantum programming, please let me know. Okay. Otherwise, I will. Yeah.
Yes, sir.
Any questions?
Yes, I would take the question. So the first question is, sir, it's from Chiranjit Pal. It's sir, can you suggest few names of books on quantum machine learning? And sir, I would like to add on to this question, as in, what are the resources you would recommend for quantum computing as well, and quantum machine learning besides?
Quantum machine learning, I don't know any book is available or not. I think there might be some new books, but most of there are very good research papers are available both on quantum neural network. If you are telling that quantum machine learning, a lot of activities has been done in quantum neural network. Regarding quantum computation, there is a phenomenal book of Isaac Chuang. Okay, okay, people can study that book. It's a Nelson Chuang book, and also there are a lot of lectures which are available online. The pretty phenomenon of the lectures of Peter Shaw and David Deutsch from Oxford, and Peter Shaw from IBM. They can look into these are the two phenomenal algorithms, Deutsch algorithm and Shor's algorithm. And I think that means apart from Nelson and Chuang, there are other very good. There's one book authored by Marmin. That's also a very good book. So a lot of books are available in the quantum computing, but in terms of quantum machine learning, I think you have to still start with some of the very good research works which are available in IEEE or SCM, or the journals like quantum information and computing from Internet Press and all this. Yeah.
Okay, sir. Thank you, sir. And go to the next question. It's from Shujit De. What does transpilation mean? Please describe shortly.
Okay. So as I told that, suppose when you are writing a high level program, right? Suppose C, and this high level program, okay, when you try to execute in your processor, right, it is broken down into micro instructions, okay, through a sequence of compiler and assembly operations. Very similar to this is also transpilation. So you have a high level circuit, okay, the high level quantum quantum description in terms of quantum gates and quantum network, circuit network, right? And when you try to map it to a particular technology, right, the technology has its own constraints, has its own primitive quantum operations. So, so there is a transformation which happens, okay, either ordering of qubits, because you know that, okay, these quantum systems physically does the job. So to do the job, you need to order your qubits to the quantum resources of the systems. So you require a sort of ordering which is called a placement. Okay, and also the gate library what you have in a particular technology, okay, maybe a bit different, okay, from the library what you are using in a high level quantum flow. So this particular transformation of your quantum description from your high level to your machine level form, okay, can be called as a transpilation. Okay.
Okay. Yes, sir. So next question is from Dola Gupta. Sir, what can be considered as a prerequisite for getting into quantum computing?
Okay. So if you are doing quantum computing, okay, obviously knowledge of quantum mechanics will be always be very handy for you. You can go through some of the that will one course on quantum mechanics to understand what's a quantum domain, right? You also have to know linear algebra, okay, and complex domain, because linear algebra and complex domain are the basic the basic mathematical framework of quantum computing. Okay, rest all is obviously you have to know algorithm. So I think any, that means I think if you want to explore the quantum, okay, quantum computing, right, from computer science background or electrical engineering background, right, okay, you need to go through at least 3 courses: so quantum mechanics, linear algebra and complex field, and this and yeah, obviously algorithm, because because whenever you try to describe an algorithm of quantum domain, you need to compare it with the classical counterpart, right? And you have to show it's, that means if it is better, okay, or if it is not performing better. So to do, you need to have a strong hold or to understand the flavor, you have a strong hold of algorithm analysis. Yeah.
Okay, sir. Sir, I would like to add to this, and it's a question from Oshwarya Borik, I guess. How much knowledge of quantum mechanics is required for getting started?
Okay, so it's very difficult because this is a very interesting subject, but as that means as for a that means for a beginner level, or you just want to kickstart your quantum computing, right? I think you need to know the basic quantum postulates in terms of okay, the superposition, entanglement, and interference. This postulate should be very clear to you. That means you have to have the Hamiltonian operation Hamiltonian field. Okay, that you have to know, and you also have to know some of the operators in the quantum domain. How you measure the quantum state, that means how you measure the probability of a quantum state, right? In terms, okay, those mathematical postulates of quantum mechanics, which helps you to understand the state measurements. Those, I think, the key areas of quantum mechanics you need to understand.
Okay, sir. Okay, sir.
Okay,
Perfect.
so
So next
let me
question
go.
is from
Yeah.
sir. There are a few more questions. So would you
So
like to
what
take
I will
them
do,
now or at
I
the end?
will, yeah, yeah. So I will let me go to the demonstration of the program of the programming environment, and then I will again come back and then I will then again come back
Okay.
to the technical questions. Okay. Okay.
Okay. Sure thing. Perfect.
Okay. Thank you. So let me. So some of you, if you have compute, that means if you are online with computer, you could just work with me. Yeah, it's obviously you need to install the Qiskit, which I'm not showing here because it's a bit long process. But but just follow me. So this is my Anaconda prompt, and I will just Just one sec, huh? Just give me a bit time. Okay. Okay, so I'm sharing my so uh, so this is my Jupyter notebook, which is starting. Okay, and I will just go one by one. Okay, my notebook is visible to all of you, right?
Yes, sir.
Can
Yes,
all
sir.
of
It's
you?
visible.
Okay, okay, great. Yeah. Uh-huh. Okay, so let's actually do some very preliminary labs. Okay. So is the font size is okay, or you need to increase this font size? Is it okay?
Um,
Now
I
is it
think
okay?
yes, sir. It's okay now, I guess.
Okay,
Yes.
okay. So if you see that if you have Qiskit package installed in your okay Anaconda, you can just import this particular uh, Qiskit Qiskit, and you can start. This is a Python 3 notebook. Okay, and see that this is a very simple way to define a quantum circuit. Though there are different possible ways. If you see, a quantum circuit is a particular function, right, by which you generate any instance of a quantum circuit. Okay, and when you give a number here, it means it's a 3 qubit. That means any quantum. That means, again, if you remember my in my present my one of my lecture slide, I have shown that when you try to define a quantum system, okay, it is actually a system consisting of how many quantum bits, because the gates or the operations that you do is nothing but the evolution of this quantum register in time. Okay, so whatever you will be initializing or you will starting with is a set of quantum register, and that means a particular quantum register, which is nothing but a set of qubits. Okay. Now, so this is this is an operation H, and I think you know what is an H. H is basically, okay, the superposition operation, okay, and this is called a Hadamard operation, right? And if we do an H, and this is a single qubit operation, so you do H, okay, on the 0th qubit, right? And when you do a 2-qubit operation, which is basically a controlled operation, now this means that this is actually a control followed by target. So when I write CIRC.cx, so CX is again from the get library, like we had the H is from the get library supported by the Cascade package. Okay, it's a Hadamard get. CX is also from the get library of the Cascade package, and this is called a control NOT. X is basically NOT, and CX means it's a control NOT. So when you have a control NOT, it is a 2-qubit operation, right? And this 2-qubit operation is the control qubit is the 0, and the target qubit is a 1. Second is actually your
excuse me, sir. Sorry for interrupting.
Yes.
There's a request from the comments to increase the size of the text.
Or increase
so that
further,
it's
okay?
Yes.
Okay.
Yes, sir.
Okay. Now is it okay?
I think so, sir. Yes, sir. This would be perfect.
Okay. Okay. So.
Okay, sir.
So this one, so this operation is CRC.cx, which is again a control NOT operation, and this is actually the control is on the 0th qubit, okay, and this is on the 2nd qubit. So we have three. The 3rd qubit. We had the 3 qubits. If you see the initial description, we have 3 qubits. So that the qubit indices are 0, 1, 2, and 3. Now, if you want to, let me try if I can show this. Okay. I can show this. Oh, sorry, I didn't run this. Okay, so you see, this is the circuit. Do all of you can visualize this? Can see this circuit? So this is the circuit what I have drawn. I have constructed.
Yes, sir. Yes, sir.
Okay,
it's visible.
great. So this is the Hadamard gate on this, and this is the control NOT gate, but the control is on the 0th qubit, and the target is on the 1st qubit, and this is the control on the 0th qubit, and target is on the 2nd qubit. Okay, so this is the way you can simply construct a circuit. I think with these tools, you just need to know that what are the gate libraries available in the Cascade package, and you can just initialize your circuit with a number of qubits by this particular instruction, and then you can just build up the circuits okay, by this particular instruction, and then you can just visualize the circuit by circuit name .draw, and you get the circuit. Okay, so I think this is, I think now everyone here will be able to construct his or her circuit on, that means on the basis of the circuit description what I try to achieve, right? Next is that how we simulate the circuit. Okay, so how we simulate this circuit. So for simulating this circuit, or to evaluating the result of the circuit, okay, what you need to do, you need to actually okay, so invoke a simulator. Okay, invoke a simulator, and and this AER is called an high performance simulator, Cascade simulator. Okay, there are, I think, more simulators, but I think this is one of the good simulators you can always use. So this is the simulator which you are calling, which is called AER, and this AER can also have a lot of okay, ways. As you are doing it on Python, you don't require okay, that okay, this okay, that means you can just use the state vector simulator, right? If you are not, as you are not doing it on the machine, you can just call the state vector simulator. So this is the backend description, what you need to define what is your simulator. And then once you have defined your simulator, there are some more options of simulator. Okay, you can actually okay, look into the manual of this IBM Cascade, and you can look into the different forms of simulator you have. But just for this particular lecture, I am trying to focus on one simulator here, which is the state vector simulator. So this is the way how you invoke the simulator. What do? You actually define a job, right? And you execute the circuit with the backend simulator, right? And you actually generate the result, and you try to push it into a variable result by calling the job.result, and then you define the output state. The output state is a state vector, and all the vectors are represented by 3 bits, 3 values upper decimal. So the precision of the state vector. So this is the precision of the state vector, right? The precision of the state vector is 3 values upper decimal. So if you run this, okay, if you run this, okay, you will see this is the description of your state. Now again, come back to my discussion. So what is quantum computation? Quantum computation is that you start with a state description at time 0, which is the initialization. If you don't initialize, it will be all will be 0. Okay, all the gates will be 0, right? And then after a time interval, right, this will be operated at this and this. So then you come to the final state of your system. If you stop here, if you stop in this part, okay, you come to the final state of your system, which is shown in the result. So your result consists of, okay, your result consists of actually 1, 2, okay, sorry, this is 1, okay, 1 state, this is 2nd, this is 3rd, let me see, okay. 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay, so you see that these are the 7 states. Okay, so the first state is represented by 0.707. It's actually, if you just compute, it's 1 by root 2. So the first qubit is in the superposition of 1 by root 2, and the complex part is 0. Second is both the real and imaginary is 0. Third is both the real and imaginary is 0. Fourth is 0. Fifth is 0. Sixth is 0. Okay, right? And then the last one is again 1 by root 2 plus the complex part is 0. So you see that what you need to understand from here is that all the states, okay, are essentially can have a real and a complex part. Okay, and that's why you can always define a phase component for a quantum state. right? Your amplitude will be, what is your amplitude? Amplitude will be your root over real square plus imaginary square, right? Right, and your phase will be tan inverse imaginary by real. So this is the way how you can have a phase and amplitude of all of your the quantum bits, right? And that's why you need to understand the complex domain very well. Okay. Now, if you want to plot it, there is a standard Cascade visualization uh, uh, visualization um, uh, function, which you can call the plot state city. Okay, and you can see that. Okay, you can see that these are the real coefficients of the states. You have the 7 states, right? You have the 7 states, and for state, okay, for state 0 you have two peaks. Okay, one is on the okay, real, okay, okay, and then on the imaginary, all are zeros. Okay, on the imaginary, all are zeros. So that's the way you can actually try to understand. Okay, right, and then you can go on like this. You can also represent it as a matrix. So if you want to represent the quantum circuit as a matrix, okay, this is the matrix of the quantum circuit. That means, what is the quantum circuit? Quantum circuit is actually H, X, and X. Okay, now there is a way how we can evaluate the quantum circuit for matrix process. I'm not okay trying to explain you it great details, but what you need to do, you need to actually, okay, if you have no gate in one particular, okay, sorry, let me see if I can have anything here. Okay, so the normal understanding is that if you have no gate in the qubit lines in a particular time size, in a particular timeline, you can just put identity operation. You can just put identity operation here. So this will be I and this will be I. Similarly, this will be I here and this will be I here. So now you can actually do a sort of tensor product between the gates in the same level, and a vector product between the gates between the two levels. And by this, you can actually generate the matrix of your circuit. Okay, and if you do that, you will see that this is the matrix of your circuit, unitary matrix of your circuit, because this will be a unitary matrix, and as it is of 3 qubit, it will be of size 8 cross 8. So this matrix will be of size 8 cross 8, 8 rows and 8 columns. You can go on like this. Okay, yeah, that means, and you can go on like this. So this is one of the understanding I have tried to give you, that how you can generate a quantum circuit, right, in your okay, using a very simple simple instructions what are available, and calling the functions what are available in the Cascade packet. Next, I will actually describe you one algorithm, okay, which is pretty interesting algorithm. And before going into the coding part of the algorithm, I just want to explain you the algorithm. Okay, so let me go back to my presentation once again. Okay, so this is the algorithm what I will be trying to explain you. Okay, this is called a Grover search algorithm. What is a Grover search? I have tried to explain it in the best way. Okay, what it does. So Grover search is actually finding an element, okay, among a list of elements. Suppose we have a list of unsorted list of n elements. Suppose I need to search whether a given element is present in the list or not. And suppose I am trying to use a classical algorithm. So the way I try to do is that I will try to take the input to be searched, and I have to compare that with each of the elements in my list. And the worst case, okay, and in the worst case, the classical algorithm will be of the order of n, because I can reach to the last element of the list, and then I can find the search is true. In the average case, it may be n by 2, and in the best case, it may be 1 in the classical. Vis-a-vis, if I try to do it in the quantum, that's why the quantum supremacy is root n. Okay? So, in the quantum, we have a quadratic speed up, because from the worst case, okay, from the worst case, which is actually linear, right? I have made it square root order. So it's a quadratic speed up. It's a squared order speed up. Okay. Okay. Now how I achieve this? This achievement is done by two operations. One is the oracle operation, which is shown here, and two is the amplitude operation, which is shown here. So what the oracle operation does? So also there is one important aspect here. See, when we try to do it in the classical, so now the question may be very simple, that, sir, how you reduce this complexity? What's the core component of quantum algorithm that reduces this complexity? My answer is, let's try to use superposition. Let's see how superposition helps me in this algorithm. If you look into this particular part of the algorithm, which is here, what it does. In the case of classical, if you want to search, okay, you have to go to each element in each of the call. Suppose you have a sort of comparator. Okay, now the comparator, how many calls you need to do for the comparator? In the classical case, you need to, at the worst case, you need to do the n calls of the comparator, right? And this comparator is normally called as an oracle. But in the case of quantum, due to the superposition phenomenon, what I can generate a superposition of qubits. Suppose my n is 16. Okay, suppose my n is 16, which means that I have that means an unordered list of 16 elements. So what I can generate, okay, I can generate a superposition of 4 qubits, right? And the superposition of 4 qubits represent me the 16 values. Okay, and that is the superposition what I have shown here. So you do it in one shot, right? And then the oracle, what is the oracle? Oracle is a comparison. Means that I think here we have 8. Okay, let us try to check. I think this is an 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it means that I have produced, so here the number of qubits is 3. So we started with 3 qubits, and we generate a superposition of all the qubits, and we generate 8 states. Now the oracle does a comparison. That means in the oracle you compare with your state, right, and your superposed state. Okay, and remember, all these comparisons are done concurrently because the state is superposition state. Means that if you were okay, if you were operating, okay, if you are operating an F, okay, on a superposition of states, the output is the superposition of the outputs where F operated on all individual states. So as your input is superposition, your output is also a superposition of all the outputs, right? And this is also done in one shot. Now the only difference between all the output states, okay, is one particular output state whose phase is inverted, right? And this state is called a mark state. See, so this is called an M and M. This M and M is for the mark state. So all the other states will not have a phase inversion, but for the mark state, you have a phase inversion. This minus alpha M means the mark state will have a phase inversion. So this is the beauty of the Oracle algorithm or Oracle function. So still we are away from our results. Still we cannot just tell that, hey, I do a measurement, I will get it. Why? Because a quantum state measurement is nothing but the square of the amplitude. So though its phase is inverted, but this particular state has the same amplitude as that of all the others. So you cannot just measure here, and you cannot just tell that, hey, I have found a different, I have already marked this particular state, and if I measure, I will get it. Because it's not that, because the probability of all the states are same. Because though the amplitude, though the phase has been reversed, but the amplitude is still the same. So square of all the amplitudes are all equiprobable. So you cannot show. So in measuring this, there's an equal probability of all these states. So what you need to do? You need to do a sort of amplitude amplification of this state, such that the amplification of this state makes the amplitude of this state higher, very, 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 very high compared to all the other states, right? And this amplitude amplification, once you do the amplitude amplification, okay, fine, and if you measure, right, you will get to this particular, the probability of this state is higher. So when you try to do the measurement, your entire state will collapse to this state, because this state has a higher probability due to its amplitude is much higher than other states. And that is what Grover's search algorithm tells us, right? And if you try to understand this geometrically, what actually happens, okay, if you look into this is your result state, okay? This W is your result state, right? And this is actually your state, the state of your system, right? And this is the mark state M. What this amplitude amplification does, this amplitude amplification, okay, actually tries to, okay, sorry, not, okay, sorry, let me recollect, okay. Okay, sorry. This is your marks. This is your result state R. This is a state which is complementary to result state. Okay, and this is your actually state of your state of your system. So now what do you want to do? You want to make the state of your system closer to the result state, and that's your goal. right? And this is the representation in terms of your probability distribution, and this is a representation, geometric representation. So what it does, it actually reflects this state, okay, on the complementary of the result state. This is the perfect orthogonal to the result state. So you first reflect this and bring here, and then what you do, and then you reflect this on this. So this then goes to here, right? And again you then you again reflect this on the complementary, which will be somewhere here, and again you reflect this here, and this will come here. So by repeated operations of your of this operation, this actually generates this particular state, which is close to the result state. Okay. Okay. So let's actually that is. So I hope you have understood what is the quantum operations which are required to do this. Let's try to go back to my to the Jupyter notebook and try to check what is there. Okay. So okay. So if you look into this, so this is an example. I will just go very briefly. This is an example list. Okay. This is an example list where I define my, this is an example list I first initiate. Okay, that means I initialize the list with some random values. And just to make my computation worst, what I do, I define a winner, which is my search element, as 21. And this is my oracle function. What's the oracle function? The oracle function is that if my input is winner, then the oracle will return true, otherwise false. Okay, right? Now this is the classical execution. Okay, let me run this, and you see that I have given the value 21 as the winner, which is at the last of the list, and this list is, I think, of 13 elements. So index position is 12, and the number of calls to the oracle is 13. So it's a worst case, because I have strategically chosen the winner as the last element of the list. Okay. So this is what is the classical algorithm. Now, if we try to do it in a quantum, what happens? In a quantum, I will try to make it a little bit simpler task. Okay. So what I will do, okay, first of all, I have to, so the oracle, what I am using here is that I am trying to, okay, let me define the oracle, and the oracle here is okay, this is actually first of all, it's a 2-qubit oracle. So 2-qubit oracle means I can have states 0, 0, 0, 1, 1, 0, 1, 1. And let's try to define the, let's shorten this. Okay. And so let's try to define the problem like this. Okay. So let's try to have a 2-qubit oracle. So a 2-qubit oracle means you have state 0001 1011, and suppose the winner is 11. So now this oracle, which is CZ01, this oracle is the control is 0 and target is 1. And what this CZ does, CZ is actually flips the uh, bit, okay, flips the bit if the flips the target if the control is 1. Okay, sorry, flips the target if the control is 1 and target is also 1. So what it actually does, this actually tries to change this particular state. So if we apply CZ over 1 this will result to -1 1. Okay, so this is the operation of the CZ gate. Okay, if the control is 1, it flips the target. Okay, so let's see that means what's the CZ gate works up. So this is a CZ gates. Sorry, I didn't run this. I think I didn't run this one, escape part. Okay, so let's run this cascade and see. This is the CZ operation, CZ gate operation. Okay, and then let's try to check that this is my simulator now. Okay, this is my simulator. Okay, as I told, the state vector simulator. And what I do, I define a quantum circuit, and first I do the superposition. So this is superposition. Okay, as it is a 2-qubit circuit, I'm doing a superposition. Okay, and I'm operating H both on the 0th qubit and the 1 qubit. And then the oracle, what I have created, this is the oracle. Okay, the oracle is a CZ gate, and this oracle is only for the 1-1 state. Bind it. I'm making the problem very short. So 0001 1011, and this oracle is being prepared in such a way, a control Z operation where the control is 0 and the target is 1. That is the 1. Yeah, that is 0th qubit the control, and the 1th qubit is the target. I prepared in such a way that it will do the phase inversion of only the 1-1 state. And this oracle I am calling in the circuit. So you see that I have defined my own gate, custom gate oracle, and I am just bringing that gate using the append function. Okay, and I'm telling that the oracle will be applied on the 0th and the 1st qubit. And then I am again drawing the particular circuit just to have a look that how the circuit looks. Okay, so this is the circuit, right? And I have given 2 measurements. Okay, okay, this quantum circuit 2 means I have 2 quantum bits, right, and 2 classical qubits. Okay, right. Let's try to start with now I simulate this. Okay, now I simulate this. You see what has happened. If you can look into this, this is a superposition. Why? Because if you try to see this results, this operation is actually 1 by 2 0 sorry 0 0 0 1 1 0 and -1 1. So this particular operation, this particular circuit, because Hadamard on 2 qubits will result to this output, this Hadamard superposition will result to the state which is 1 by 2, 0, 0, 0, 1, 1, 0, and 1, 1. And on that, if I apply the oracle, it will generate minus on 1, 1. So you see that when I generate the oracle and I get the value of my state is something the same. Okay, it's 1 by 2, it's 0 0.5, 0 0.5, 0 0.5. So this is 1 by 2, 0, 0, 1 by 2, 0, 1, 1 by 2, 1, 0, and minus 1 by 2, 1, 1. So the intention of marking this particular 1, 1 state has happened through this particular oracle. Okay. Okay, now let us go on. I will try to, and now this is the next operator, which is called the reflection operator or quantum amplitude quantum amplitude operation. And this is the circuit of this. This is the sequence of H, Z, and control Z and H operations again. I'm not discussing this in much details. So if you try to draw this circuit, I don't know why it's not working, but so now you have two blocks of the circuit, right? One is the oracle and one is the reflection, right? And now if we try to make the entire quantum circuit, what you need to do, you need to define the quantum circuit as two quantum bits and two classical bits. Okay, you first call the Grover's search. Okay, you first call the Hadamard superposition, then you use the oracle, then you use the reflection, and then you do the measurement, which is on the 0, 1 basis. So we measure, so this 0, 1 measurement, this is a 0, 1 basis, and we measure both the qubits, 0th qubit and first qubit. And let's try to draw this circuit. Oh, sorry, I'm making this, sorry. I have stopped this. So let's see. This was the circuit of the amplitude amplification or reflection. This is the circuit, which is the entire circuit of the oracle and the reflection. And now you can just find the results. Okay. And this is, you see that what happened is that the 1, 1 state. Okay, this is a very, very ideal setting. The 1, 1 state has been raised to maximum amplitude of 1, and all other states are 0. And that's okay because you know that you need to run 2 times. Okay, this particular application, because you have 4 states. So 4 states means root over 2 times you have to do the reflection operation, right? And that is there, and so you can get, actually we have done 1 reflection operation that itself is giving a very good result. Okay, so this is the way that what I am trying to show you is that is most important is that how you can describe your own gate here using the basic operators, how you can append the gate in the larger quantum circuit, and how you can ultimately simulate this circuit. Okay, and that's all the Chasm platform gives you. The Qiskit platform gives you. Now I just want to show the last part of this. What I have shown until this is the Qiskit part which you do in your own Python. Okay, Python terminal, right, in your Python platform in your own local computer. But you can also run the Qiskit in the IBM cloud platform. Okay, for that, what you need to do, as I have shown, you need to create an account, and there is a token which will be created once you create the account. Okay, and this token you need to copy, and you need to place it here. You need to run this particular. I have already have the token, so this is there. So you have to run this particular managerial stuff first. Okay, you have to call the Qiskit import IBM Q, which is the IBM cloud, and you have to give your token, and you have to execute this, right? And then you can get several data of your platform, that you can say what is your account, what are the providers of this particular IBM account, and then you can just run the same quantum code, okay, as you have seen, as you have already learned. Only the thing is that you have to write one more line, which is called provider equals to IBM.load account. And if you do this, okay, say this particular example, what I'm running, this is running on the IBM backend. Okay, this is running on the IBM backend. Okay, see, and this is the these are the values what I have got. Okay. Okay. So yeah, so this is what I have got. So this is actually okay, 495 is the probability of 00. So this is actually 0.495, and 0.505 is the probability of 1. Actually, this is preparing a Bell state. This is actually preparing a Bell state, which actually generates our entanglement of 0, 0, and 1, 1. This is a circuit which does that. Okay. So you see that using the real IBM platform also, you can just run the same code. Only you have to invoke the IBM account, and you have to call the IBM account while you're simulating, and you can get this. And these are the all details you can get. Okay, these are the more examples. I'm not showing you due to the limitation of the time. See, you can see all your parameters. What is your simulator? What is your job ID? And this job ID will be stored against your account, right? Okay, and this all you can see. So see, this is the date and time. I think this was a previous execution, and sorry, I didn't execute it. Okay, let me just execute it once. Sorry, let me execute. So job ID, job result, see, job creation date. So now it is 17th April, and now it is I think 6:23, and that's what is telling, and other parameters. Okay, so this is and this is okay. Sorry, so this is the description. When you give this command that backend, okay, try to invoke the backend, you will get all this. So you have okay, n qubits, 32 qubit system you are having. Okay, you can have backend version. Okay, all these gets are available. This is the get library which you can have, okay, in your circuit, right? You can have all the list of the get libraries. You can have a maximum short. So what is the short is actually the number of iterations you can do on the circuit, because normally this is a probabilistic computing. So when you tell probability, if you just do one execution, if you get the result, whether it's fine, no, you can have a large number of run, and then you can take the average of that run. So that is the short. So experiments means how many executions you can do. Okay, how many discrete executions you can do, right? And this is all the parameters you can get, and this is what is IBM Q platform. But anyone interested to know more, okay, you can connect my group and connect me, and I think we can give you okay, a good help or good knowledge for the different algorithms that you can run in this discrete platform. Okay, so I end up here. I think it is maybe a bit extended, but I thought that okay, I should give you the exposure to create interest among the students. Okay, to get into this particular activity. Okay, so now I stop my sharing, and
yes, sir. Thank you, sir. That was it. And it was a great lecture, sir. Sir, there are a few questions in the comment section. Would you like to
Sure.
take them up or?
Yes, yes, yes,
Okay.
please.
Uh,
Please, yeah.
okay. So, firstly, there's a question from Nitesh Agarwal. Can
Yes.
be utilized for mechanical system control.
Yeah, can you just repeat once again? What's the question? Yeah.
Yes, how quantum coding can be utilized for mechanical system control.
Okay. So, so differential equations are basically one of the backbone of okay, of mechanical systems, right? And there are beautiful algorithms for solving differential equations, and we are actually working not on the mechanical control domain, but in some other aspect. We are working uh, to solve the differential equations on the quantum computing platform, and so essentially problems of mechanical systems can be ported into the quantum algorithm, and they can be executed in a quantum system. Yeah.
Okay, sir. So the next question is from Debajyoti Datta. How quantum logic can be implemented in the classical hardware?
That's a good question. Okay, so there is a domain called reversible logic, okay, which actually covers a subset of quantum, okay, subset of quantum logic, okay, in terms of hardware. But the true quantum gates cannot be implemented on classical hardware, though though we can generate programming instances on the classical hardware which can execute quantum functions to some extent, okay, within a limit. But if you are telling that how we can generate a classical hardware, true hardware, which will execute the quantum functions, okay, only the reversible functions can be implemented through your CMOS logic gates. But two classical functions, two quantum functions cannot have an hardware equivalence in the classical domain, but they can be simulated, okay, in a classical hardware system.
Okay, sir. Thank you, sir. The next question is from Sriparna Ganguly. Where should I start if I want to learn quantum cryptography from the scratch?
Okay, very good question. So you should
She is
you
from
should
background.
okay, so you should actually have a preliminary course on cryptography first of all, and then you can start taking up the QKD problem, okay, which is called the quantum key distribution problem, which is basically how the symmetric key cryptography can be taken in the quantum domain. And you will see that there are a lot of work has been done at present on the QKD. There is a BB84 algorithm, and there are other algorithms which implements QKD. And then you can try to look into some of the quantum encryption techniques. Okay, you can go step by step.
Okay, sir. Thank you for answering. Well, there's a question from Sriparna Ganguly again. She wanted to requested to re-explain things, but I think we are just, Sriparna, we highly
You
apologize
can you
on
can do
our
it
end.
offline. You can do it by mail or through
Yes, we
LinkedIn.
are.
You can connect with them.
Yes, the recording of this lecture will be shortly available on this channel. And if you have any other questions or queries, please feel free to connect with Dr. Amlan Chakrabarti on LinkedIn or reach out to him through his email ID. Aditya, could you drop them in the comment section? The LinkedIn and the email ID handles. Yes, yes, they are. Thank you. And before we end, make sure you subscribe to our YouTube channel and follow us on handles. The link to our Facebook and LinkedIn pages will be provided in the comment section below. Apart from this, we are bringing forth to you a feedback form. This form will be active till the next hour. Please go ahead and fill it. This would be of great help for us. Well, this marks the end of today's session. And on behalf of everyone, I would like to thank Professor Amlan Chakrabarti again for taking time out and being here today. Thank you. Thank you so much, sir. It was a great learning
Thank you.
experience. And
Thank you.
and for everyone else, thank you for supporting us by joining in. These are trying times as India is battered by severe COVID-19 second wave. We wish our audience that they observe safety and follow all social distancing norms. For our next webinar on 24th April, Saturday, we will be having Saisoon Kim from the University of Oklahoma. This will be the final lecture of the series on quantum computing for beginners, academia, and industry. Until then, stay safe. Goodbye. We hope to see you again next time.